Here we have an animation of 4 balls falling near Earth. Let's watch it. Let's watch it in slow motion. Do you notice any difference in the way the balls fall? Do you notice any difference in the balls themselves besides the material they're made of and their masses? You should notice that we have these arrows pointing downward from each ball. What do these arrows represent? Well, they don't represent velocity because each ball has the same velocity as the others. They don't represent acceleration because they all accelerate at the same rate. These arrows represent force. They represent the weight of the balls. Remember, weight is the force of gravity pulling an object toward the Earth. Let's look at this table where we see the force of each ball and the mass of each ball. Now, what happens if we divide force by mass? If we divide force by mass, we get 9.8. The unit is newtons per kilogram. Here we have 28.42 divided by 2.9. We also get 9.8 newtons per kilogram. 9.8 newtons per kilogram and 9.8 newtons per kilogram. Now, what is newtons per kilogram? Remember, a newton is a kilogram. Let's say 1 newton equals 1 kilogram meter per second squared. So if we take newtons and divide it by kilograms, the kilograms cancel out. And so we can say 1 newton per kilogram is equal to 1 meter per second squared. Each of these values is therefore equal to 9.8 meters per second squared. Remember Newton's second law, F equals ma. Force equals mass times acceleration. So if we take this mass and we multiply it by this acceleration, because it's in meters per second squared, it's acceleration. We take this mass, multiply it by this acceleration, this mass, multiply it by this acceleration, then we get this force or this weight. This leads to, or this agrees with Newton's second law. Gravity provides constant acceleration on an object. Gravity is always a force that pulls 2 objects together. Some forces can push or pull. For example, a spring, it can push or it can pull. Gravity, on the other hand, gravity is a force that acts in one direction. It pulls 2 objects together. Gravity is the force of attraction. Anything that has mass has a gravitational field around it. And when the gravitational fields of 2 objects interact, there is an attractive force. We are all in Earth's gravitational field, and so we are all attracted to the Earth. Remember, mass is the amount of matter in an object. So mass is a scalar value. When we measure things in kilograms or grams, like when we put them on a balance, we're measuring their mass. We're measuring the amount of matter in that object. However, weight is a vector. Weight is the force of gravity pulling an object toward the Earth. In most cases, it's the Earth because most of the time we're dealing with objects on the Earth. So weight actually changes with distance from the Earth. When something is close to the Earth, like we're all close to the Earth, our weight is greater than if we were far away from the Earth. The farther you go from the Earth, the weaker your attraction to the Earth. And so weight changes with distance from the Earth, or weight relative to the Earth changes with distance from the Earth. But your mass doesn't change. If you go up in space, you go up to the moon, your mass is going to be pretty much the same as it was on Earth. The only changes are going to be things that you take into your body or that are removed from your body. The moon is smaller than the Earth and it's less massive than the Earth. So that's why when you see videos of astronauts walking on the moon, they're taking these giant steps because they are experiencing lower levels of gravity. The moon has a significantly weaker gravitational field. This is a force diagram. A force diagram is different from a free body diagram. Remember, a free body diagram shows only the forces acting on one object. That's a free body diagram. A force diagram will show hopefully all of the forces in a scenario. In this case, we have a car crashing into a wall. So we have the force of the car on the wall. This is how I am abbreviating these, with 2 letters. And then we have the force of the wall on the car. Okay, what other forces are there? Well, there's going to be a force of gravity. So that is, to stick with this convention, that's the force of the Earth on the car. And then there's a normal force of the Earth, the Earth pushing back up on the car. Erase that. Well, no, I'll just do this. So we have the force of the Earth pulling on the car, and then we have the force of the road pushing up on the car. Okay, so the Earth is pulling the car down. The road is pushing back up on the car. This is the normal force. The force of the Earth on the car is the gravitational force. We're going to not worry about friction right now. We have the wall has weight too, right? So we have the force of the Earth on the wall. Then we have the force of the normal force, so the force of the road on the wall. Now, there may be other forces. There may be a force of friction. There may be, the car may be accelerating toward the wall when it hits it. So it may be pushing against the road, but we would be making assumptions if we put those forces in. So we're just going to say the car is not pushing on the road. The road's not pushing on the car with any net force that would cause acceleration of the car. So we have an action reaction force pair. And the action and reaction forces are the force of the car on the wall. The car hits the wall hits the car. The force of the car on the wall, the force of the wall on the car. That's an action reaction force pair. And it doesn't matter which one you call the action and which one you call the reaction. It makes logical sense to say the car hitting the wall is the action because the car is moving toward the wall. But together they make an action-reaction pair. Here we see a golfer hitting a ball. Let's see how Newton's three laws of motion apply to this scenario. The first law of motion says an object will remain at rest or in uniform straight line motion unless acted upon by an external force. So the ball was sitting, we can see that a bunch of sand flying. So the ball was sitting in the sand trap until the golfer hit the ball. The golfer exerted an external force on the ball, and so the ball changed its motion. So it went from at rest to in motion. Newton's second law says an object acted on by a net external force will accelerate in the direction of that force according to the formula A equals, this letter is sigma. Okay, it means the total, the net force. So the acceleration equals net force divided by the mass. That is exactly what we just calculated a couple of slides ago for those falling balls. We took the force and we divided by the mass. That told us the acceleration of those objects. This ball is experiencing the same thing. It has a force exerted on it, and so then it accelerates away from the club. So it accelerates in the direction the club was striking it from, and that the amount that it accelerates is inversely proportional to its mass. So if it was a heavy ball, it would not fly as far as if it's a lighter ball, or it would not accelerate as fast. Let me say that correctly. It would not accelerate as much as if it was a lighter ball. And Newton's third law says for every force, there's an equal and opposite reaction force. So when the ball hits the club, when the club hits the ball also hits the club with the same force in the opposite direction. The golfer can feel that. That's why the golfer can feel when the club hits the ball. Now, the ball did not remain at rest, nor did it enter into uniform straight line motion, right? When a club hits a golf ball, the ball's, let's say here's the club. It's a badly drawn club, but that's okay. The ball is going to go in a parabolic arc, right? It's going to become a projectile. So it's not in uniform straight line motion. So what net external force acted on the golf ball after the club hit it? Well, the only force acting on it after the club hit it, because it was in free fall, right? Once it was a projectile, it was in free fall. The only force acting on it was gravity, gravitational force, the force of the earth on the ball. Or we sometimes call it F sub g for force of gravity. Okay, but the force of gravity is constantly pulling it down, and that's why it follows that parabolic path. So let's say this player hits the golf ball for a time t, because the ball doesn't fly away instantly, right? The club pushes it with a force F. The ball is at the origin. After it leaves the club, it moves upward at an angle in the positive x and y directions. What equation or equations do you need to solve to find the initial velocity of the ball after it leaves the club? There are two equations you're going to need in this case. The first one is the acceleration is equal to the velocity, the initial velocity, divided by the time of the hit. The second one is going to be that the acceleration is equal to the force divided by the mass of the ball. And the second one, that should look familiar, because that is just a rewriting of Newton's second law of motion, F equals ma.